So in today's video we are going to learn about inter-process communication. Okay, so in the previous video we had just started out with Linux system programming. So while parting the video I had asked a simple question like the output that I was getting. Okay, so this was just like demo. I wanted to ask is what output I am getting and what I should get. So here if I write my name, so the name and the hello command that I had kept was intended to have a space between this thing. So here I have written the string hello and that I have wrote to the standard output. Okay, and after that I have written the user input. Okay, so I have taken test. Okay, so here I had asked why I'm not getting the space over here. So the question or the answer to that question is because I have given the wrong size over here. Okay, so here I have given only 5 characters. Okay, so that is why. So the crux of this thing is the size, or you could say the size of the last part that you do is the critical part. Okay, so if you mess up the size part, okay, and you give a wrong size, then your characters will not be printed out properly. Okay, so similarly like we did now in the upcoming videos also, we'll be using a lot of write command and read command. Okay, so make sure whenever you're using the write command or read command, you just verify the sizes that you're giving. Okay, so that you don't mess up in terms of reading the data or writing the data, because these things can lead to something called as segmentation fault. Okay, so either you will be accessing the memory that you don't have available, or maybe you will be writing over memory that you don't have available. Okay, so you can either read from a wrong location or write from a wrong location. So both these cases are unintended and they have unintended consequences. So that is why we should be careful. So now moving over to the current video. Okay, so in this video, as I said earlier, we'll be learning about inter-process communication. So why exactly inter-process communication is needed in the first place? So when we create any kind of application, so like if you consider systems application, so to give you an example, so like if you are writing like a program is there, so like it was about to send some data over the Ethernet or any sort of a thing. So you have a web application, okay, that communicates through another systems application that in turn communicates with another application that actually sends the data. Okay, so this kind of structure usually exists in enterprise applications because the role of applications is divided. Okay, so like one application is intended for some other purpose, some other application is intended for other purpose. Okay, so this application work in collaboration. So to ensure the best collaborative effort, we use something called as inter-process communication. So that is what we call a core feature any of the operating systems provide. Okay, so in our discussion we'll be generally restrict ourselves to Linux. Okay, but somehow you could say the same kind of mechanism is available with different names, of course, maybe a different terminology, but available in other operating system platforms as well. Okay, so now to get started, so today we'll be discussing specifically in terms of IPC, we'll be discussing about pipes. Okay, so pipes are, you could say, the core fundamental, or you could say the basic or the most easiest way you could implement inter-process communication between two different processes. Okay, so firstly, why pipes are used? So you must have if you're familiar with Linux, you must have used pipes before. Okay, so any kind of application, what you do, like any kind of application, like you are doing history, for example, like I have written history, so I have like hundreds of commands over here. Okay, so I want to search like git commands. Okay, so or like GCC command. So what I am doing is history parallel pipe, sorry, and grep GCC. Okay, so this will show me what kind of things I have done with this thing. So here basically what I am doing is I am doing a pipe over here. So output of history is sent to this process grep, that is a regular expressions parser or that sort of a thing, and it will search this keyword GCC in the output that I have already given. Okay, so this was just an example to show what exactly pipes accomplish. Okay, so there are two types of pipes basically. So one is a simple pipe and another one is called named pipe, or you could say FIFO. Okay, so we'll implement both. Okay, just to show you. So firstly we'll start with called as simple pipe. Okay, we'll name it simpipe.c. Okay, so to get started, firstly, like always, you will need stdio.h. Okay, then you will need what you call unistd.h. Okay, and after that we'll write main. Okay, and here we'll have to create two file descriptors. So as I've said earlier, like in Linux, okay, when you're using Linux, so everything is a file. Okay, so any kind of system operation, any kind of device driver, anything that you are accessing, reading, writing, that will be a file. Okay, so files will have file descriptors which will be what you call integers. Okay, so that is why I have created two descriptors. One will be for reading and one will be for writing. Okay, no, even that is not right. So one will be the child and one will be the parent. Okay, so the idea of pipes is it is a unidirectional thing. Okay, so here when we talk about the file descriptors, we are essentially having, you could say, two different files. One for this thing, what you call the parent, okay, and one for the this thing, the child process. Okay, so internally it manages two routes. Okay, so these are two different files. Okay, so if you do the pipe command, it will take care of both these things. Okay, so we'll write the pipe command here. So pipe, sorry, and fd. So you see here, if you see, so this is a one-way communication, and here it will show you two. So like one file essentially takes care only of the read part and one file takes care of the write part. So one file is read only, one file is write only. Okay, and this, like they said earlier, like they have said in the documentation here, create a one-way channel. If successful, two descriptors are showed. Okay, on byte 0 and 1 they will show you. Okay, and if successful, 0 is returned and -1 if not. Okay, so what we'll do is we'll just check this condition then. Okay, we have written fd and we'll put a if condition around it. Sorry, so with if condition we'll check if the value is -1, so to check like whether we have messed up something or due to any system error it is not able to create the pipe. Okay, and here we will write pipe creation failed. Sorry, pipe creation failed. Okay, and here we shouldn't proceed as the program will fail. Okay, so here I will do a non-zero return. Okay, so remember when you're writing C program, so return 0 usually means your program exited successfully. Other than 0, any number that you give will be a error. Okay, so make sure you follow what you call the semantics of this thing to your day-to-day programming habits. Okay, yeah, so moving forward, so here we have successfully created the pipe. Okay, so now what we have to do is we'll have to split the flow into child and parent. Okay, so this is how we do it. So we create a PID, sorry, we do a fork. Okay, so what fork does it? Let me just cover this documentation. So clone the calling process, exact copy it will create. So the exact process table entry and all these things will be copied. Okay, and return -1 for errors. Okay, 0 for the new process. Okay, so this will give us the process ID. If it is if this thing fails, okay, then it should return -1. Okay, so this is the magical part. So now here I am checking if that thing failed or not. Sorry, if PID is -1, that has failed, right? So here we will write P error again, process fork failed. So it was not able to fork a child process. Okay, and so again we will return 1. Okay, you can return different numbers. You can return 1 here, return 2 over here, like that is fine. It is an error, so it is up to you what interpretation you want to give for that error. Okay, so after that, once you reach over here, now here we'll write PID 0. Okay, so PID 0 over here is the child process. Okay, so let's just take this over here, child process. Okay, and in the else block we will be getting the split flow of the parent process. Okay, sorry, this keyboard is not in the right state, I suppose. Yeah, so yeah, so just add it, sorry, return 0 at the last, sorry, and okay, so here we head over to this place, and what we do now here is we need to make sure that we close the read end first. Okay, so here we close FD 0. Okay, sorry, because we are not going to read from this end. Okay, we are going to write from this end, so that is why this thing will be closing, and only after closing we'll be able to read. Okay, so that is important. Okay, if you don't close the file, you will not be able to read the file. Okay, so buffer will not be cleared, so that is why you need to close the file. Okay, so here you write my message is hello. You can write anything you want. Okay, and yeah, so like you're good to go. Now when you write your message, FD of 1. Okay, so this is the right channel. Okay, message, and here size of, and here you write message, sorry, message. Okay, so again after writing your message, you just close the file descriptor 1 as well. Okay, so now you have written your message. Now it's time to read your message. So here what we'll do is the inverse process, because now I'm reading, I need to close the right channel first. Okay, so if it is open, it will close, right? Yeah. So now you take the buffer over here, and in this buffer what you need to do is you write the read command and read the data from the file descriptor 0, okay, into the buffer. Okay, and here you provide the size of the buffer. Okay, and after you have read this thing, if parent received message, and here you write %s, which is this thing for string, okay, and you can put a new line, buffer, okay, and here you write this thing, and after you have done the reading part, you close ft0 now. Okay, so essentially these two are different flows. Okay, so here your process has split after this fork command. Here there are two split parts, so whatever is being executed, this is in two different processes. Okay, so there is a parent-child relation over here. Okay, so this one is the child process. So when the PID is 0, it is executing in the child process. If it is something else apart from obviously -1, it will be in the parent process. Okay, so the newly created process, child process will have a process ID of 0 for this thing, and with reference to that it will have a parent process connection ID. Okay, so let's not worry about it at this point. So now to run this program, what we'll do is we'll just simply write to one second. Okay, so we have compiled this thing, and now if we write, so we should receive that message over here. See here, parent received the message. Okay, so here you have written the message, so you can clearly see we have not even used the same variable. See here, we have written the data from the message variable. You have used the write command and close that string descriptor, and here we have used the read command and read from the another descriptor. Okay, and this we have read over here. So this thing is the simple pipe, as I told you. So this has its own issues. So it is a half duplex thing. Okay, so it doesn't actually send complete data, full cycle you cannot communicate in, and also there are issues in terms of deadlock in this case, and you have very small buffer size that is available, so that is what causes the deadlock in this case. Okay, so for that purpose, and this is strictly the parent-child relation should be there. Okay, so that makes things difficult. Okay, and that is why we have something called as named pipes. So we'll start with an example of named pipes. So for the named pipes, we will actually need two programs. Okay, so named pipes are much more flexible. Okay, so they are known as FIFO as opposed to the simple pipes. Okay, so they can have or handle bidirectional communication as well in cases. Okay, so we'll be not using the bidirectional channel ability of that thing, but we'll be demonstrating how that things work. Okay, so let me just create two files. One is sender.c and another one is receiver.c. Okay, so simply what we'll do is create a sender that will send data and the receiver will receive that data. Okay, so in the previous program we had done it in the same file itself, so here we'll be doing it in two different processes. Okay, so the constraint with simple pipes is that you needed a parent-child relationship. Here it is not mandatory to have a parent-child relationship, so any unrelated process can also communicate with another process in this case. Okay, so this is truly what you call the IPC method that people use. Okay, so to get started, here are a few things that we need to know. So implicitly this thing has different types of what you call parameters, or you could say files that need to be maintained. Okay, so for that purpose we'll need a few file handles. Okay, so here what I will do is constant char pointer p4, and here we'll create that file tmp -fifo. Okay, and this file will serve as the FIFO. So you might think like this is just a simple file, so how will it act as a FIFO or named pipe? And pretty much what is the difference, like why we are not using a regular file? So the regular file takes up disk space, that is your hard disk space. Okay, so to avoid getting your hard disk clogged, you will be using simply RAM when you use this thing, the FIFO, that is the named pipes that we'll be using. They'll be purely working on the RAM. Okay, so that is why they are much more faster. Okay, so there are cases when your swap space or that kind of place is being used in some cases, which is actually the hard disk space, but that is also like it happens through the paging process and all those things. So like explicitly the FIFO works through the RAM itself. Okay, so it makes it fast. So the first function that we'll be using over here, like to differentiate this from any other file, we'll be using mkfifo. Okay, and here once we assign this file, so this mkfifo has two parameters. One is the file name and another one is the permission. So we are giving it 66666 permission. Okay, so these are read and write permissions. Okay, so that we have given. So after that we'll create again a file. Okay, and for that we'll be using open, and this time we are going to write in that file because this is a sender. Okay, so write only. So here you might see that we are getting this red wavy line and all because we have not imported things. So let us do that. Okay, so fcntl. Okay, see here, so file control functions are in fcntl. Then as always we need unistd.h. for this FIFO thing we will need sys/stat.h, and finally we might need we'll be using strings to pass things here and there, so we'll be using string.h. Okay, so let's continue. So now, like we did previously, we'll check whether this returns like -1. Sorry, -1 is the error, you can say. So if it returns -1, then we throw the error. Okay, so like p error opening file, and return 1. So here when we return 1, that is means unsuccessfully this program was executed, or like the program failed essentially. Okay, so yeah, so continuing, now that we have to transfer the message, hi from sender. Okay, and here we'll write that to the file descriptor, message and strlen and message. And here a slight change that will be required is we have to add a +1 to this thing, because strlen function returns only the length of the string. It does not consider the null terminator that is included at the end of string, because in C or C++ the string, or you can say the character array, is terminated by a \0. So usually it is not visible in the actual string that's you defined, but it is necessary. If you don't add the null terminator, then you might get segmentation fault at the receiver end. Okay, or even the sender end as well. So just make sure that you are avoiding such mistakes. Okay, and now printf sender send message and we'll just display that message. Okay, and we'll close our file, close FD. Here we opened it. Okay, now we are closing it, and we'll just return 0. Okay, and now in the receiver is just like inverse of this thing. Okay, so we just copy this part, like whichever is like replication part is there, so we'll just copy this part. Like there's no point in writing this whole thing again. So like the sender will be reading from the same file. Okay, so this will be sender, that will be the receiver. Okay, and here I'll be reading the same file. The only difference that we have over here is the descriptor. Okay, so I'll be not creating this FIFO. So this FIFO, the MK FIFO part would be created by the sender. Okay, I'll be just at the receiving end. So here what I'm going to do is, instead of write only, I'm going to do read only. Okay, and if I write FD equals to -1, just like this, sorry, I'll just copy this thing now. Error opening file. Okay, same thing. Like in the two programs, you will find like the same thing is done in the first few lines, and now the only differing part will start from here actually. So here, just like the program that we did for simple FIFO, simple pipe, not FIFO, we create a buffer. Okay, in that buffer we'll read that data, read FD and buffer and size of buffer. Okay, so after reading, so what this read system call will do is, it will see how many bytes are available in the file descriptor, and it will write those bytes, or you can say read those bytes into the buffer. Okay, and from there we can print it. Okay, so we'll add a print F for this thing. Received message, we'll say, and %s, sorry, %s and buffer. Okay, and after that we'll also close this FD. Okay, and return 0. And let's just compile. Hopefully we'll be having no errors, because I think this thing after a very long time. Okay, thankfully no errors as such. Receiver. Okay, and now I've compiled these two programs. Let me just open two terminals over here. So here you can see the two terminals. Okay, just placing them side by side. Okay, I've opened VS Code in one. So the idea here is you have to run the receiver first. Okay, you can't run the sender first, or if you run the sender first, then you need to be like flash speed fast to open the receiver before even the message is sent. Okay, sorry, Linux system does not have receiver. One second. Okay, receiver, it does have a receiver. Sorry, no such file or directory. One second. Okay, so yeah, so here I should have opened this thing, the file mkfifo I should have done in the receiver, so my bad. So here it created the file, so that is why I was getting no such file or directory. Okay, so once that FIFO file is created, so this is how things run. Okay, so hopefully I was able to explain you how the IPC through pipes works. Okay, so in the upcoming videos I'll try to improve the kind of presentation that I have a bit. Okay, thank you.